Hi, I'm Professor Melko, Chemistry PhD, and your university chemistry professor. Have you ever wondered, why don't oil and water mix? And you've just wanted a simple explanation?
Actually, through the miracle of science, that can be arranged.
Great! I'm here to give it to you. Let's jump into the lecture and learn something about solutions, the like dissolves like rule, molarity, mass percent, and dilutions. Let's start the lecture. So, let's learn about solutions. As the saying goes, if you're not part of the solution, you're part of the precipitate, what falls out of the solution as a solid. But inside the solution, you're a mixture of two or more substances, and you're a homogeneous mixture. Okay, this is a definition we learned earlier in previous videos. Feel free to go back and read up, or watch up, I should say, the videos on mixtures, substances, homogeneous versus heterogeneous. But the solution is always a homogeneous mixture of two or more substances. So one of the substances, there's a lot of. There's plenty of it. The thing in greatest abundance, we call that the solvent. So here in my little diagram, maybe these are little sodium chloride particles that I'm putting in water. Water here is the solvent. There is mostly water. And these little particles I'm putting in, maybe they're sodium chloride particles, a little bit of table salt I'm pouring into water. That would be the solute. So whatever there's most of, that's the solvent. Whatever there's least of, that's the solute. And a solution is always made up of these two things, solute and solvent. Okay, there can be more than one solute, right? I could also have potassium chloride, right, or sodium fluoride, other substances, sugar, sucrose I could put in here. Those are all solutes that are living within this water solvent. Together, everything is called a solution. Now, really we have two different types of solvents, and this explains what types of solvents mix with other solvents and what settle out, kind of like oil and water. A solvent that's composed of polar molecules is a polar solvent, pretty self-explanatory. And we learned about polar molecules in previous videos. Remember, if two elements differ in electronegativity, like maybe H and Cl, these differ in electronegativity or how badly they want an electron, so this represents a polar molecule. In the same way, hydrogen and oxygen have different electronegativities, so water is a polar molecule. And so if the solvent is water, that's a polar solvent. Okay? And there are lots of different types of polar solvents here. Some are listed in the table. Methanol, ethanol, acetone, water, for example. You can also have solvents that are composed of nonpolar molecules. Things like hexane, heptane, toluene, etc. So these are made up of elements that have similar electronegativities, so there is no really hogging of electrons in the molecule by one element as opposed to another, like there is with water. And these hydrocarbons, okay, or even carbon tetrachloride, this molecular geometry, all the chlorine atoms end up wanting the electrons equally, and there's no net effect. So overall, this CCl4 molecule is nonpolar overall and makes a nonpolar solvent, right? This chlorine up here is counteracted by this chlorine down here, so there's no net, uneven distribution in of the electrons in this molecule. Whereas HCl does have this chlorine that is hogging all the electrons in this bond, and overall the molecule is polar. Okay, so we can have polar and nonpolar solvents. And the like dissolves like rule tells us what substances will mix with other substances. So like dissolves like means if both are polar, they dissolve in one another. If both are nonpolar, they dissolve in one another. Okay, that's the like dissolves like rule. Polar liquids dissolve other polar liquids. Okay, polar liquids will not dissolve in nonpolar liquids. Okay, when you mix a nonpolar liquid with a polar liquid, you do not form a solution because it is not a homogeneous mixture. Right here, there's oil that's sitting on top of water. Right, this is not homogeneous throughout. There's clearly a separation here. Right, and that's because oil is nonpolar while water is polar. Okay, so this is the rule we use to sort of decide whether a solvent is going to mix and create a homogeneous mixture with another solvent to make a solution. Now, we have some vocabulary on what a solution is, a solute mixed with a solvent, and we learned something about certain solvents dissolving other solvents, or mixing, I should say, with other solvents. But how do we express the concentration, right? Exactly how much oil are we trying to put into water and failing to make a solution? Or, more likely, how much, say, sodium chloride are we putting in water and making a solution? What is the mass percent of that solution? And what is the molarity of that solution? Those are two frequently used measurements of how we might communicate to other scientists what the concentration of that solution is. Right? The concentration is how much solute it's dissolved in a given amount of the total solution. Okay, so keep in mind here that it's always solute over solution, not solvent. It's not solute over solvent. It's solute over total. Mass percent is the first one we're going to look at, and this one makes the most sense if you understand what a percentage is. It's always part divided by a whole times 100. And it's no different here. Mass of the solute divided by the total mass times 100. That is the mass percent. So let's look at an example. If I dissolve 5 grams of sodium chloride in 97 grams of water, what is the mass percent sodium chloride in the solution? First, let's try to identify the solute and solvent. 5 grams NaCl, 97 grams of water. Remember, whatever there's less of is the solute. So here, sodium chloride, there's less than water, less sodium chloride than water, so that is the solute. Okay, water is the solvent. There's more of it. What is the mass percent of this solution? Well, I take the solute here, 5.00 grams, and divide it by solute plus solvent, right? It's a common mistake to just put 97 grams here in the bottom, just accounting for the solvent. But we need both. We need the whole solution. So it's really 5 grams plus 97 grams. And all of this ratio times 100. So 5 divided by 5 plus 97 times 100, I should get 4.90%. That would be the answer to this practice problem. So that's mass percent, one way we communicate how concentrated a solution is. Solute over solvent. Grams of solute over total grams times 100. Molarity trips people up a little bit more, but this is the most commonly used unit of concentration for solutions. Okay? The abbreviation here is capital M. So whenever you see a capital M, that stands for molarity. You might see 6M, 6 molar solution. The molarity is 6 molar. That's the terminology we use. We calculate it like this: moles of solute over liters solution. Again, here it's always solute over solution. But here we're talking about moles of solute, not grams. So make sure in molarity, use moles. Okay, this makes sense if you just remember this capital M molarity. Sounds like we need moles involved. Okay, so just make sure you're converting any grams of solute into moles of solute. So you take this moles of solute divided by liters, not milliliters, not cubic centimeters, not picoliters, just liters. Has to be liters. Moles of solute over liters of solution. That's molarity, capital M. So let's look at an example. What is the molarity of a solution containing 24 grams of sodium hydroxide and 100 milliliters of solution? Okay, so molarity, I need moles of solute. So I know this amount of solute I'm given here, the sodium hydroxide, I have to convert to moles. 24 grams of sodium hydroxide, convert it to moles. I should be pretty comfortable with this by now, given grams of sodium hydroxide. I know that unit goes in the bottom, so I cancel it out. And I'm trying to convert this to moles. I need the molar mass of sodium hydroxide. So I add up 22.99 grams per mole for sodium, 16 grams per mole for oxygen, and 1.01 grams per mole for hydrogen. And I should get something like 40.00 grams sodium hydroxide per 1 mole sodium hydroxide. Okay, 24 divided by 40 is 0.600 moles sodium hydroxide. So that's step 1. I've converted the solute from grams to moles. Done. I need liters of solution, 100 milliliters. Maybe you can do the conversion in your head, or you have to write out 100 milliliters converted to liters. Well, there's 1,000 milliliters in 1 liter. milliliters goes away. .100 liters is 100 milliliters. So my molarity overall is 0.6 moles divided by 0.1 liters, or 6.00 molarity NaOH. Okay, so that's how I would express this final answer. The number to 3 sig figs, 6.00 capital M for molarity NaOH. So that's mass percent. Molarity, again, for molarity, make sure you have moles of solute, liters of solution. Okay, always convert grams to moles of solute. Right, always convert solution to liters before you try to divide out this ratio. The last concept to discuss here is dilutions. Okay, often in the lab we're going to make some solution that's called a stock solution, from which you're going to dilute down to make weaker solutions. So diluting means we're adding more solvent only. Okay, the moles of solute are not changing. Okay, so maybe you have this 6 molar sodium hydroxide solution, and that's sitting in a beaker. We can make 1 molar sodium hydroxide by taking a portion of that more concentrated 6 molar and diluting it down. Okay, so this is dilution. Here's shown a serial dilution, taking 10 mils of this stock solution, filling it up to 100 mils total with solvent is one dilution, and you can then do a dilution from that to another dilution. Each time you can see the color is getting less and less dark. It's getting lighter as the solution becomes diluted. As far as calculations, the molarity of the first solution times the volume you're taking of that first solution is going to equal the molarity of the second solution times the volume of that second solution. So M1V1 equals M2V2. This looks really familiar to another law we talked about back in a couple previous videos. P1V1 equals P2V2. This was Boyle's law. We're kind of doing the same thing here, just with molarity instead of pressure. Initial equals final. M1V1 equals M2V2, where M1V1 are the initial molarity and volume, and M2V2 are the final molarity and volume. So let's look at a typical question. What volume of this 6 molar sodium hydroxide solution needs to be diluted to prepare 5 liters of 0.1 molar sodium hydroxide? Okay, students often get tripped up with the wording here. Just recall the formula and try to identify what are a molarity and volume that are connected. So what volume, that's a V1, of 6 molar, that's an M1, needs to be diluted to prepare 5 liters, that's a V2, of a 0.1 molar, that's an M2, sodium hydroxide solution. And now we plug in the numbers, okay? M1, 6.0 molar. V1, that's what we're after, equals M2, 0.10 molar, times V2, 5.00 liters. And now we simply solve for V1. Divide both sides by 6 molar. Your molarities should drop out here. And 5 times 0.1 divided by 6. I get 0.083 liters. Okay, which should come out to about 83 milliliters. I'm doing 2 sig figs here since that's what I was given in the problem. 2, 2, and 3, so I go with the least number here, following the rules of multiplication for sig figs, and present 2 sig figs in the final answer. Okay, so that's a dilution calculation, always M1V1 equals M2V2. Okay, that'll do it for this video on solutions. We covered like dissolves like, mass percent, molarity, and dilutions of solution. As always, please feel free to like this video and subscribe to my channel on YouTube, or catch me over on Twitch where I do weekly office hours every week answering your chemistry questions. I'll post another video on practice problems for this material. Until then, that's all for today. See you next time.